Okay, 3.6.2, we're not necessarily really learning anything new. This is more just a revisitation of Dirac delta notation, which we covered way back, right? And this entire section is sort of dedicated to treating Dirac delta notation, but with a different sort of viewpoint. And sort of the point that we're going to try to make here is that writing Dirac notation, but treating it sort of in more detail, gives us a pretty unique ability to look at some of these mathematical setups and elements that we've encountered so far and sort of rewrite them in more nuanced and interesting ways. So without further ado, let's get started by just introducing or reintroducing the bra-ket notation, right? So way back at the beginning, we introduced inner product, and we said, okay, I can write inner product as bra alpha ket beta in this bra-ket notation, where this is the bra, which is the first half of the bracket, and this is the ket, which is the second half of the bracket, right? And what this actually means is ultimately just a way of rewriting in a more compact way an infinite integral of alpha star multiplied by beta dx, assuming that these are functions, right? Alternatively, if these are vectors, then this is just alpha 1 star times beta 1 plus alpha 2 star times beta 2, so on, so on, so on, so on. So sort of the thing that we're going to look at here is we're going to look at the idea of, instead of treating the bra-ket as an entire thing, sort of considering what would happen if we started looking at the bra and looking at the ket and like sort of treating them as if they were separate elements. And what we mean by that is, well, what happens if I split this into an individual bra and an individual ket, right? Does this have any significance? Well, if I look at this, right, is there any way for me to break this up into two disparate parts? And hopefully you already see it, but sort of automatically the ket beta is just going to directly translate to beta itself. So ket beta is just a direct translation to beta. However, ket or bra alpha, right, this thing can sort of be looked at as an integral from negative infinity to infinity of alpha star, but with, this blank thing times dx, where I'm sort of waiting to accept something in front of the bra in order to get like my actual integral. And this is sort of, very similar to the way operators work in linear algebra, right? In linear algebra, if you have an operator q hat and you're operating it on some sort of vector, or I guess not vector, but like a matrix, this is going to give you like an entirely, if you act on matrix 1 with an operator, this gives you a new matrix, matrix 2, right? In the same way, right, this is sort of the functional analogy, and by functional I mean like the version that uses functions, right? This is the functional analogy for an operator, because what this is doing is this is going to say, okay, alpha is this element where if you apply it onto some function, right, if you do this, right, this is going to give you a new function, function 2. So in that way, you can sort of treat bra alpha, and just the bra in general, as sort of this equivalent to an operator in function space. And this allows you to write some pretty interesting things. And once again, we're not learning anything new. We're just going to be introducing a few ways of working with this sort of notation and seeing some interesting things that result if you play around with this a little bit. So immediately, the first thing we're going to introduce is a new type of operator, and it's called the projection operator p hat. And p hat is going to be defined as ket coming in front of the bra, right? So we're used to, the opposite order. We're used to a bra and then a ket, but if I write the ket in front of the bra instead, I get this weird thing that's called a projection operator. And what this does is it's going to measure how lined up two vectors are. It's going to give you a new vector that is sort of a projection of the first vector. And what I mean by that is, let's, for example, right, apply p hat onto some random vector beta. In this case, this is going to give me ket alpha times the inner product of alpha with beta, because the bra and the ket make an inner alpha, right? And in that case, if you are doing this, well, this is an inner product. Remember from way back then, we learned that the inner product is just a measure of how lined up two vectors are, right? If I have one vector alpha and I have some other vector beta, and let's say that beta lies halfway. This is the halfway point along alpha, and this is equal to 1/2 times the magnitude of alpha, right? What that means is that the inner product is going to give me just 1/2, right? Because what this is saying is, the inner product is once again a measure of how closely aligned one vector is to another. So if one vector is directly 1/2 projected onto the other vector, your inner product is going to give you just the coefficient, which is 1/2. Now, if this 1/2 is then applied onto the vector alpha, the original vector, this is going to give you 1/2 times the vector alpha. That is literally just, forgive my ability to not draw straight, that is literally just this vector, right? So the projection operator is going to be applied onto a vector, and it's going to give you a new vector that is sort of the projection of the vector you're applying onto beta onto your original vector alpha. So this is something that inevitably will become very useful when you start using Dirac delta notation a lot more in more complicated problems. But for now, we're just going to leave it at that. Griffiths is just going to leave it at that. And we're going to do one more thing. We're going to say, okay, projection operators actually have their own pretty unique property, which is that if you add up a bunch of different projection operators in terms of orthonormal bases, you get the identity matrix. And what I mean by that is I'm going to claim this new thing. I'm going to say, okay, let's assume that I have this basis of orthonormal vectors E sub n spanned by n, right? So that means that the inner product of any individual basis with another is going to be equal to Dirac delta of m sub n, right? So in this case, what I'm going to say is, okay, if this is the case, well, the sum of the projection operator of every single one of these orthonormal bases is actually going to equal 1. And I'm going to further say, if this is the case, this implies that this thing is equal to the identity matrix. So once again, we haven't proved anything yet. We're just claiming that this is true. So if this is in fact true, well, how do we prove it? Well, we know that the identity matrix multiplied onto any operator is just going to equal the operator itself, right? So if we want to see whether or not this is true, let's multiply this by a vector, right? So summation n of projection operator in terms of these orthonormal bases multiplied by alpha, right, is going to equal alpha. I'm going to say, is this true? Well, if I write this out, right, this is going to be E1 vector times the inner product of E1 alpha plus E2 vector times the inner product of E2 with alpha plus blah, 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 blah. And, this is going to give me alpha 1. This is going to give me alpha 2 in terms of, the individual matrix elements of alpha. So this is going to give me, alpha 1 times the vector E1 plus alpha 2 times the vector E2 plus blah, 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 which is literally just the definition of alpha, but expanded in terms of the bases that you're used to describe it. So if this is true, then that means that sort of this summation term must equal the identity matrix. And the rest of this section is sort of a clarification on the technically correct way to write certain vector forms, which I'm not really concerned about to actually elaborate on. That gets more into math and less into physics. So I'm just going to skip that and go to the last part of this section, which is another sort of thing where it's like we're just going to sort of get introduced to something, and Griffiths isn't going to bother to prove it because the actual mathematical proof is going to be too math intensive and complicated for this point, assuming that you're at this point in the course as, I don't know, like I believe at this point you would be upper division quantum mechanics, right? So at this point, he's going to say, okay, well, it's not worth it to try to do this proof, so I'm just going to throw this fact at you, and it's that if you encounter a function in terms of an operator where the operator is treated as a variable, such as, for example, something like e to the power of q hat, or q has an arbitrary operator, he's going to claim that you can actually expand this in terms of a power series where you're just treating the operator as a variable. You can say, okay, I can expand this into just, the standard power function of e to the power of x, but I'm just going to use q hat instead of x, so 1 plus q hat plus half q hat squared plus blah, 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 right? And he's going to say, okay, you can do this with any function that involves, operators as variables. So I can do the same thing with 1 over 1 minus q hat. I can do the same thing with natural log of 1 plus q hat, all that stuff. And we're not proving it. We're just going to take his word for it for now, because we are too much of math babies to sort of have the proof actually be worth it for us to learn, considering that this is a physics course. And we're going to leave it at that. So that's 3.6.2. Once again, not really learning anything, more so just introducing sort of hey, look at this, an interesting way of looking at bra-ket notation and sort of seeing a glimpse of sort of the implications of what would happen if you were to work with it in more detail, and seeing and sort of understanding that, by recognizing, the projection vector and sort of this unique way of writing the identity matrix, there's some unique and weird tricks that you can do with bra-ket notation that you can't really do with, more standard mathematical models, things like functions or matrices and stuff. And sometimes it might be advantageous to work entirely in bra-ket notation. What those situations actually are, we don't necessarily know yet, but once again, this is sort of a sneak peek. It's sort of a glimpse into some of the math that would be possible once you do this switch, and once you would actually encounter a system that actually requires a switch like this.